So we will delete the old code to print the scan tokens and replace it with this. Here we have parser, space parser equal new space parser parameter tokens closing statements. And the next statement, xpr space expression equal parser.parse empty parameter method closing statement. So the next statement, this will stop if there was a syntax error. So if parameter had error, return closing. Then next statement, system.out.print in parameter new space AST printer method dot print parameter expression closing statement. So this is in logs.java. Notice we jump to logs.java in run method. So we replace the 5 lines for that. Now congratulations, you have crossed the threshold. That really is all there is to handwriting a parser. We'll extend the grammar in later chapters with assignment, statements, and other stuff, but none of that is any more complex than the binary operators we tackled here. Note, it is possible to define a more complex grammar than logs that's difficult to parse using recursive descent. Predictive parsing gets tricky when you may need to look ahead a large number of tokens to figure out what you're sitting on. In practice, most languages are designed to avoid that. Even in cases where they aren't, you can usually hack around it without too much pain. If you can parse C++ using recursive descent, which many C++ compilers do, you can parse anything. So fire up the interpreter and type in some expressions. See how it handles precedence and associativity correctly. Not bad for less than 200 lines of code. So again, precedence, how the operator will precede each other, and associativity, if the same operator precede each other. Challenges. In C, a block is a statement form that allows you to pack a series of statements where a single one is expected. So again, in C, a block is a statement form that allows you to pack a series of statements where a single one is expected. So a block is a statement form. It's not a statement. So it allows you to pack a series of statements where a single one is expected. The comma operator is analogous syntax for expressions. So the comma operator is an analogous syntax for expression because everything you hit comma, you're entering a new expression. So a comma-separated series of expressions can be given where a single expression is expected. So a comma-separated series or combination of expression or series of expression can be given where a single expression is expected, except inside the function calls argument list. So this is not in the function call or method argument list where you might have expect the comma separated expression. So at runtime, the comma operator evaluates the left operands and discards the result. So at runtime, the comma operator evaluates the left only and then discards the remaining or its right side. Then it evaluates and returns the right operand. So add support for comma expressions. Give them the same precedence and associativity as in C. Write the grammar and then implement the necessary parsing code. Likewise, add support for the C-style conditional or ternary operator, question mark colon. What precedence level is allowed between question and colon question? Is the whole operator left associative or right associative? Add error productions to handle each binary operator appearing without a left-hand operator. So again, you would add error productions to handle each binary operator appearing without a left operand. So we still need to represent a rule, an error production rule that will handle a case where the binary operator are without a left operand. So in other words, detect a binary operator appearing at the beginning of an expression. Report that as an error, but also parse and discard a right-hand operator with the appropriate precedence. Not just produce an error, but since that error is the left side, is the initial that will produce a side effect of errors, you want to discard all of those side effect errors. So do that, represent that in a method and class, and then with the requirements that it also must follow the appropriate precedence in the precedence table. The sign note, logic versus history. So let's say we decide to add bitwise and or operators to locks. Where should we put them in the precedence hierarchy? And most languages that follow in C's footsteps place them below equal. This is widely considered a mistake because it means common operations like testing a flag require parentheses. Like this, if parameter flags and flag underscore mask equal sum underscore flag, then closing parameter, and then inside the body, this statement is considered wrong. So what considered right is if parameter with a open parenthesis flags and flag underscore mask closing parenthesis equal sum underscore flag, then closing parenthesis or the closing parameter of if, and then an empty body, which is correct. Should we fix this for locks and put bitwise operators higher up the precedence table than C does? There are two strategies we can take. You almost never want to use the result of an equal expression as the operand to a bitwise operator. So again, you almost never want to use the result of an equal expression as the operand to a bitwise operation. By making bitwise bind tighter, users don't need to parenthesize as often. So you don't want to use the result of the equal operation expression as the operand to a bitwise operator to avoid the user having to use open parenthesis and closing parenthesis often. So if you do that and users assume the precedence is chosen logically to minimize parentheses, they're likely to infer it correctly. This kind of internal consistency makes the language easier to learn because there are fewer edge cases and exceptions users have to stumble into and then correct. That's good because before users can use our language, they have to load all of that syntax and semantics into their heads. A simpler, more rational language makes sense. But for many users, there's an even faster shortcut to getting our language ideas into their wetware. Use concepts they already know. Many newcomers to our language will be coming from some other language or languages. If our language uses some of the same syntax or semantics as those, there is much less for the user to learn and unlearn. This is particularly helpful with syntax. You may not remember it well today, but way back when you learned your very first programming language, code probably looked alien and unapproachable. Only through painstaking effort did you learn to read and accept it. If you design a novel syntax for your new language, you force users to start that process all over again. Taking advantage of what users already know is one of the most powerful tools you can use to ease adoption of your language. It's almost impossible to overestimate how valuable this is. But it faces you with a nasty problem. What happens when the thing the users all know kind of sucks? Sys was operator precedence is a mistake that doesn't make sense. But it's a familiar mistake that millions have already gotten used to and learned to live with. Do you stay true to your language's own internal logic and ignore history? Do you start from a blank slate and first principles, or do you weave your language into the rich tapestry of programming history and give your users a leg up by starting from something they already know? There's no perfect answer here, only trade-offs. You and I are obviously biased towards liking novel languages, so our natural inclination is to burn the history books and start our own history. In practice, it's often better to make the most of what users already know. Getting them to come to your language requires a big leap. The smaller you can make that chasm, the more people will be willing to cross it. But you can always stick to history, or your language won't have anything new and compelling to give people a reason to jump over. Evaluating expressions. You are my creator, but I am your master. Obey. Mary Shelley, Frankenstein. If you want to properly set the mood for this chapter, try to conjure up a thunderstorm. One of those swirling tempests that like to yank up open shutters at the climax of the story. Maybe toss in a few bolts of lightning. In this chapter, our interpreter will take a breath, open its eyes, and execute some code. So this is a decrepit Victorian mansion is optional but adds to the ambience. So there are all manner of ways that language implementations make a computer do what the user's source code commands. They can compile it to machine code, translate it to another high-level language, or reduce it to some bytecode format for a virtual machine to run. For our first interpreter, though, we are going to take the simplest, shortest path and execute the syntax tree itself. Right now, our parser only supports expressions. So to execute code, we will evaluate an expression and produce a value. For each kind of expression syntax we can parse, literal, operator, etc., we need a corresponding chunk of code that knows how to evaluate that tree and produce a result. That raises two questions. First, what kinds of values do we produce? Second, how do we organize those chunks of code? Taking them on one at a time. Representing values. In locks, values are created by literals, computed by expressions, and stored in variables. So again, values are created by the literals, computed. So this is the math part, this is the binary part, this is where the add, subtraction, multiplication, division, computed by expressions and stored in variables. The user sees these as locks objects, but they are implemented in the underlying language our interpreter is written in. That means bridging the lands of locks dynamic typing and Java static types. A variable in locks can store a value of any locks type and can even store values of different types at different points in time. What Java type might we use to represent that? Note, here I'm using value and object pretty much interchangeably. Later in the C interpreter, we'll make a slight distinction between them, but that's mostly to have a unique terms for two different corners of the implementation. in place versus heap allocated data. From the user's perspective, the term are synonymous. So, given a Java variable, with that static type, we must also be able to determine which kind of value it holds at runtime. When the interpreter executes a plus operator, it needs to tell if it's adding two numbers or concatenating two strings. Is there a Java type that can hold numbers, strings, booleans, and more? Is there one that can tell us what its runtime type is? There is. Good old java.lang.object. In places in the interpreter where we need to store a logs value, we can use object as the type. Java has box versions of its primitive types that all subclass objects, so we can use those for logs built-in types. So logs type, any logs value, Java representation object, logs type nil, Java representation null, logs type boolean, Java representation boolean, logs type number, Java representation double, logs type string, Java representation string. Given a value of static type object, we can determine if the runtime value is a number or a string or whatever using Java's built-in instance of operator. In other words, the JVM own object representation conveniently gives us everything we need to implement logs built-in types. We'll have to do a little more work later when we add logs notions of functions, classes, and instances. But object and the box primitive classes are sufficient for the types we need right now. Another thing we need to do with values is manage their memory. And Java does that too. A handy object representation and a really nice garbage collector are the main reasons we're writing our first interpreter in Java. So, evaluating expressions. Next, we need a blobs of code to implement the evaluation logic for each kind of expression we can parse. We could stuff that code into the syntax tree classes in something like an interpreter method. In effect, we could tell each syntax tree node, interpret thyself. This is the Gang of Force interpreter design pattern. It's a neat pattern, but like I mentioned earlier, it gets messy if we jump all sorts of logic into the three classes. Instead, we're going to use our groovy visitor pattern. In the previous chapter, we created an AST printer class. It took in a syntax tree and recursively traversed it, building up a string which it ultimately returned. That's almost exactly what a real interpreter does, except instead of concatenating strings, it computes values. So we start with a new class, interpreter.java. So class interpreter, class space interpreter space implement space xpr.visitor with a parameter object and an empty body. The class declares that it's a visitor. The return type of the visit methods will be object, the root class that we use to refer to a logs value in our Java code. To satisfy the visitor interface, we need to define visit methods for each of the four expression tree classes our parser produce. We'll start with the simplest, evaluating literals. So, the leaves of expression tree. This is actually the leaves in the expression tree. The atomic bits of syntax that all other expressions are composed of are literals. Literals are almost values already, but the distinction is important. A literal is a bit of syntax that produces a value. A literal always appears somewhere in the user's source code. So a literal always appears somewhere in the user's source code. Lots of values are produced by computation. So again, a literal always appears somewhere in the user's source code. So lots of values are produced by computation and don't exist anywhere in the code itself. Those aren't literals. So the source code, the raw source code that is not producing value at runtime or not executing, just like doing a computation, which is what expression do, those aren't literals. A literal comes from the parser's domain. Values are an interpreter concept, part of the runtime's world. So note in the next chapter, when we implement variables, we'll add in identifier expressions, which are also leaf nodes, just like with these literals. So much like we converted a literal token into a literal syntax tree node in the parser, now we convert the literal tree node into a runtime value. That turns out to be trivial. So this is the code in interpreter.java in class interpreter. The first method at override, then below that is a public space object space visit literal xpr. So this is a method, public method parameter xpr that literal space xpr, and with the body one statement return xpr that value. So we eagerly produce the runtime value way back during scanning and stop it in the token. The parser took that value and stuck it in the literal node. So we eagerly produce the runtime value way back in scanning it using the location, the token, and then we kind of have a value there, and then we already put that into a tree using the parser. So the parser took that value and stuck it in the literal tree node. So to evaluate a literal, we simply pull it back out. So to be able to evaluate a literal, just get it out of the parser or from the visitor pattern. Now evaluating parentheses. So after the literal of that acts as a leaf of expression tree, we're now in the parentheses. The next simplest node to evaluate, or another leaf in a tree, is grouping, the node you get as a result of using explicit parentheses in an expression. So here, in interpreter.java, still in class interpreter, again, another public method. At override, below it is public space object space visit grouping xpr with the parameter xpr that grouping space xpr, and then inside would be a statement. Return evaluate parameter xpr that expression closing statement. So a grouping node has a reference to an inner node for the first expression contained in the parentheses. So again, a grouping node has a reference to an inner node for the expression contained inside the parentheses. So a grouping node has a reference to an inner node for the expression contained inside the parentheses. So a parentheses are referencing a node inside of the expression contained inside the parentheses. So it needs to have a reference there because that's what it is inside. That is what is being parameterized. To evaluate the grouping expression itself, we recursively evaluate that sub-expression and return it. So to be able to evaluate a parenthesis, to return a value, or to prepare it in runtime, we need to parse that reference value inside as well. So we need to reuse recursion here. We rely on this helper method, which simply sends the expression back into the interpreter's visitor implementation. So again, we rely on this helper method, which simply sends the expression. So again, we rely on this helper method, which simply sends the expression back into the interpreter's visitor implementation. So these parentheses node simply sends or rely on this helper method that just send the expression back to the visitor method, because remember, we're just pulling it back out from the interpreter's tree. So note, some parsers don't define tree nodes for parentheses. Instead, when parsing a parenthesis expression, they simply return the node for the inner expression. So instead, they actually don't define tree nodes for parentheses. Instead, when parsing a parenthesis expression, they just simply return the node for the inner expression instead of the outside as well, which is the parentheses. We do create a node for parentheses in locks because we'll need it later to correctly handle the left-hand sides of assignment expressions. So here, after the visit grouping XPR public method, we would add a private space object space evaluate parameter XPR space XPR with a body return XPR that accept parameter this, and then closing. So evaluating unary expressions. So like grouping, unary expressions have a single sub-expression that we must evaluate first. The difference is that unary expression itself does a little work afterwards. So here we would add after visit literal XPR method. So since this is added, there's a private, we need to add this before private and after the visit literal XPR public method. So at override, below it is public space object space visit unary XPR with the parameter XPR.unary space XPR, and with the body first statement object space right equal evaluate parameter XPR.write closing statements. The next statement would be switch parameter XPR.operator.type with a body with the first statement case minus colon. The next statement return parameter double closing parameter, then write, then closing statement for that case, then closing body. The next statement return space null, which means unreachable, then closing method. First, we evaluate the operand expression. Then we apply the unary operator itself into the results of that. There are two different unary expressions identified by the type of the operator token. Shown here is minus, which negates the result of the sub-expression. The sub-expression must be a number since we don't statically know that in Java. We cast it before performing the operation. This type cast happens at runtime when dash is evaluated. That's the core of what makes a language dynamically typed right there. You're probably wondering what happens if the cast fails. Fear not, we'll get into that soon. So you can start to see how evaluation recursively traverses the tree. We can't evaluate the unary operator itself until after we evaluate its operand sub-expression. That means our interpreter is doing a post-order traversal. Each node evaluates its children before doing its work. So the other unary operator is logical not. So here, inside the visit unary expression method, so the implementation is simple. But what is this truthy thing about? We need to make a little side trip to one of the greatest questions of Western philosophy. What is truth? So, truthiness and falsiness.